Hi everyone, my name is Abhinav Singh, and welcome to Daily Data Structures. Today, we're going to continue our discussion of hash tables from last time, and then talk about quality hashcode methods and compression functions. So before we dive in to hashcodes and compression functions, let's recap what a hash table is. The hash table is the following. It takes a key value pair, and then first, it computes the hash code of the key, where it maps a key to some integer. Then it takes that integer, or it takes the hash code, and applies a compression function, and compresses the hash code into another integer, which is basically the bucket where the key value pair is supposed to be stored. To deal with collisions, however, we need to use an array of S-lists as opposed to just an array to store all of them, which looks like the following. Let's say we have a base array of 4 in our hash table, and all of the collisions will be represented like this. Let's say there's nothing here, there's one thing here, and it basically ends up looking, like this. So as you can see, this first bucket here, or bucket in index 0, stores two key value pairs because they both ended up having the same hash code, and the compression function also hashed those hash codes to the same bucket. As a result, you had collisions. So when we discussed the runtime of hash tables last time, we found that a lot of the operations, such as insertion, removal, or find, had the potential to depend on the number of collisions that were occurring, or at least the runtime depended on the number of collisions that were occurring. We found last time that we could minimize that runtime for the insert operation by just doing insert before to an S-list when when a collision occurs, rather than running to the end and inserting at the end of the S-list, which would then make it dependent. So that way, the insertion method would run in constant time, rather than in linear time, if you used that specific trick. However, remove and find, if there are a huge amount of collisions, worst case scenario end up being in linear time. And the worst case scenario exists in a world where for some reason all of the keys end up hashing to the same bucket. So in which case remove and find would take forever. So the next question you're probably asking is, how do we minimize collisions? In fact, what controls them? Well, from the most intuitive perspective, collisions happen because keys are hashing to the same bucket. Ergo, the distribution is not even. This uneven distribution is a result of poorly designed hash codes and poorly designed compression methods, which cause the same answer to be returned time and time again. The ideal hashcode and compression function would be able to map each key to a random bucket. However, to achieve a perfect distribution is very difficult, which makes optimizing hash table something like voodoo. So you Ron Burgundies out there, watch out. Let's look at a couple of badly designed hash codes and compression functions to gain some intuition of how to design a well-made hash table. So let's get rid of all of this. So let's look at the first example. Let's say you have a hash table with the base array of 100 buckets. So the array, has length 100, or it has 100 buckets. Okay? And for some reason, your hash code maps keys to integers that are multiples of 5, meaning keys are being mapped to 5 to the power n, where n is any real number. And then your compression function is just h, which inputs a hash code, equals hash code modulo 100. So as you can see, this is a pretty bad compression function because only 0, 5, 10, 15, 20, and 25 will have entries. As a result, we are wasting the buckets 1, 2, 3, 4, 6, 7, 8, 9, 11, 12, 13, 14, 16, 17, so on and so forth. As a result, we're smushing everything into 20 buckets and having an insane amount of collisions in those 20 buckets when we could be using a lot of the buckets such as 1, 2, 3, 4, 6, 7, 8, 9, so on and so forth. And this shows that whenever you have an uneven distribution or a large amount of collisions in specific areas, then that means you either A, have a badly designed compression function, or you need to rethink how your hash code method works. So let's look at the next example where we have a bad hash code. So let's get rid of all of this. So if the previous example wasn't bad enough, then this should definitely do the trick. Let's assume that your compression function does not really compress anything. And let's also assume that we are trying to represent all the words in the English language, but for some reason we have an infinite amount of space and space is not the issue. However, what we're trying to do is avoid collisions. Now, let's assume that our hash code function takes a word and assigns each character a number. So the way the hash code works, this is just the method description. Let's say all it does is if A is equal to 1, B is equal to 2, C is equal to 3, so on and so forth, it takes the sum of all of the characters. So let's say we had the string hi, AB. So then we need to figure out so H would encode to, H would end up being encoded at 8, and I would be encoded at 9. So as a result, your hash code is 17 if you input the string hi. So the next thing is, so now that we understand what that is, let's think about why that's pretty bad. Well, the biggest reason this hash code is so awful is because things such as palindromes would hash to the same bucket. So for example, AB, or actually let's look at a more realistic example. Race car. If you spell it, it's spelled the same way forwards and backwards. As a result, if you sum the characters up, you would literally get the same hash code. Or AB would also hash to BA. Things like that. Also, there's a huge risk that smaller words would hash to the same bucket, while larger buckets would go unfilled, because you have a lot of 3, 4, or 5 letter words, but you don't have any like 20 or 22. You don't have very many 20 or 22 letter words. So as a result, there's a very large risk of collisions happening in the first few buckets, which means we have an uneven distribution of key value pairs. As a result, based off of that data, we can determine that we're dealing with a pretty bad hash code. So now you're probably thinking, how do we make the most spread out and even probability distribution so that our hash code runs in constant time? Well, for compression functions, the key is to mod with a large prime number. A large prime number allows you to create an even probability distribution, and you can see the proofs online. There's a lot of great reasons why prime numbers are so important. But this is a great example and a good rule to follow when you're designing hash codes and compression functions. In fact, if you use the Java library, you call hash codes of certain objects, they use this general formula, but p varies. So this is the template of a good compression function that you can use. H of hash code is equal to a times hash code plus b. And all of this is modded by p, and that's all modded by some number n, where a, b, and p are positive numbers, and p is prime, and also much, much larger than capital N. Or in other words, p greater than n, which I'll be reusing that notation in the future. This ensures that hash tables have a stable and even distribution. So that's it for today, and tomorrow we'll be covering amortized analysis to wrap up our discussion of hash tables, so be ready to put on your thinking caps.